Welcome back, ladies and gentlemen. We're going to be taking a look at pretty much the last topic in physics. Shouldn't take us too long, I think, because we're just going to go over it very briefly, right? We've covered a lot of details. We've looked into Newton's laws in a lot of detail. We've taken a look at momentum and impulse in a lot of detail, all that kinematics unit at the start. But this one, we're going to take it broad. We're not going to go very deep. No math. I know everyone's very happy about that. No math. We're talking about energy. Now, you kind of already know what energy is, at least broadly. Like if I say energy, you get pictures in your mind, you get ideas. Maybe you think of a mana bar from an RPG or something, or you think of like an energy drink or something. Well, energy is basically a way for physicists to simplify problems. It's a way for them to track things as they happen. It's kind of like physicists decided to sit down and say, you know what, all of this physics is cool and all, but could we make like a money of physics? Something that you can buy and sell and trade, right? If I want something to happen, I got to give you 5 physics bucks. And when I do that, that thing happens. And that's what energy is. Energy is this currency, this money, and it keeps track of and does sort of accounting, bookkeeping for everything that happens in physics. If you take a look in your booklet, you'll see, right? It talks about the fact that because energy is like a money in this case, it's sort of a way to do bookkeeping. And one of the first rules about this particular currency is the law of the conservation of energy. The idea that energy cannot be created or destroyed, but can only be transformed from one type to another. How do I transform energy? What do I mean by that? Well, basically, energy is motion. That's what it is. Energy is motion. The only question is what type of motion. Case in point, if I've got, say, my eraser over here, okay? Currently, it is sitting perfectly still on top of this counter. So currently, its energy appears to be 0. And most certainly, its energy of motion, or its kinetic energy, is 0. It's not currently moving. If I move it, then it has some kinetic energy, right? I am giving it energy. But where did the energy come from that I'm currently giving it, right? Because I can't create or destroy energy. I had to get it from somewhere else. So this energy, moving this thing back and forth, well, it's coming from me, right? I'm moving it with my arms. Where did I get the energy from? Well, I ate lunch, right? If you don't eat, you get tired. You get hungry. Food is how we get energy. Food is chemical energy, basically. That one's way at the bottom of your list, but here we go. Chemical energy. And how do you unlock chemical energy? It's very simple, actually. Let's say I take this piece of paper and I see that it's made of matter. And as we learned in the chemistry unit, matter is made up of individual atoms that are all connected together into compounds and things. And they make bonds. And those bonds have a certain amount of energy in them. So if I want to get the energy out of this, I have to find a way to break those bonds. Now, tearing the paper, while dramatic, doesn't actually break the bonds. It just turns this into smaller pieces. If I want to break these bonds, how would I do it? I'd light it on fire. Combustion releases the energy stored in these chemical bonds. And that is what's happening inside of me. We're warm-blooded creatures, right? You feel warm to the touch. Well, that means that you are currently burning food. Okay, yeah, they're cold-blooded creatures, but work with me on this analogy right now. Okay, we're keeping it simple. Keeping it simple. We'll talk about ecology later. Now, what do we see when we burn this? Is that we release energy. We get fire. And that fire will heat up the air around it. It'll make flames. Fire itself, as we've discussed in chemistry, fire is actually, the flames themselves are actually the unburnt particles of the thing I'm burning drifting away, and they glow because they're so hot. And that is another type of energy, thermal energy. It is the chaotic motion or vibration of matter, particles bouncing around super fast in random directions. That is thermal energy, or heat. You can't really see thermal energy, but you can feel it. If this was hot, if I had actually lit this on fire, I'd be able to hold my hand up and feel the heat coming off of it. Of course, the other thing that would happen if I burned this is that I would hear something. I would hear sound. And sound, or acoustic energy, is the organized motion of particles. Thermal energy, heat, is chaotic, it's random. But sound is organized. How could we show this? Well, we've got ourselves our piece of paper here. And we're going to light it on fire. Let's get some red because we're going to make it fire. Okay, and we'll put a little splash orange in the middle. That way you know it's a serious fire. Oh yeah, there we go. Mr. C's perfect drawing skills. As I burn this, heat, particles of heat, little pieces, will randomly be moving all over the place. Now, they're generally going to go away from the fire, right? Because the fire is already very hot. It's going to want to expand into places that aren't very hot. That's a little more complicated in grade 10, though, so we'll leave it for now. So it's going to randomly move like this. But at the same time, we're also going to be getting, so this is here, we'll say this is our thermal. We're also going to be getting acoustic. Because our flame, it's a little bit better of a flame. Our flame is going to crackle. It's going to make noise. And that noise is going to sort of come outward in rings of sound like this. And the further away we get, the fainter that sound will be, right? If you were really close to it, you could hear it no problem. But if you're far away, not so much. So we've talked about thermal energy. We talked about acoustic energy. Heck, we could do more. I did talk about chemical energy. Right, where we take our lump of whatever and we actually light it on fire in order to access it. Okay, here we go. We got our match. We're going to light this thing on fire in order to release the chemical energy. We also talked about kinetic energy of an object that was moving along, like this. There's also one more type of energy we haven't talked about, because I said that right now, this very moment, this looks like it's not moving, right? So it looks like it has no energy. And yet, what happens if I push it towards the camera? What happens if I push it towards the edge? It falls. Right? I pushed it, obviously, so I did do some kinetic energy there, and I moved it this way, towards you. But then it fell down. Why? It's because of gravitational energy, aka the Earth exists. Let's see if I can draw a quick Earth. Let's see, something like that. Maybe Hudson Bay down, James Bay, bring it up there. There's an island there. Maybe a piece that sticks out there like that. Yeah, something like that. Sure, that's the Earth. The Earth has a force of gravity. Let's see, what's the only color we haven't used? And that force of gravity is going to pull things towards the Earth, right? We talked about this with dynamics a little bit. Force of gravity is going to pull things to the Earth. So what happens? The object will move towards the Earth. But there's a bit of a difference between a couple of these, right? Like the thermal, acoustic, and kinetic energy are all things that are moving right now. But the chemical and gravitational, they aren't, right? Like this thing's on top of a shelf, so if I take it off the shelf and let go, it'll fall. That's how gravity works. But right now it's not falling, it's just sitting there. Similar, if I take the piece of paper and light it on fire, it will burn, but it's not burning right now. So chemical and gravitational energy kind of fit in these separate categories. We call the chemical energy and the gravitational energy potential energy. Potential meaning that it has the ability to do something, but it's not doing it yet. Now, I said energy is motion, and it is, but the difference is these two are motion that you have to unlock, whereas these three, right, these two here and this one, is motion that's already happening. So if we go back to the money analogy, what we're looking at is that the kinetic energy, the thermal energy, and the acoustic energy, the sound energy, they're kinetic, so they're like money in your wallet right now. The chemical energy and the gravitational energy is money in your bank account right now, right? Like you'd have to have your bank card to be able to take it out, to be able to use it. You don't have it on your person right now. You have to unlock it, just like you have to unlock these two. So this is sort of the basic idea behind energy. It's a way for us to track things and how they move. We saw that a bit with momentum, and this is kind of the extended version. Energy allows us to talk about things beyond just an object moving, which is really just this category. But now we have so many more options available to us. This isn't even all of them. This is just a decent set. So let's try using them, right? Let's take our understanding, hopefully our growing understanding of energy, and we're going to apply it to something we've already seen before. The Newton's cradle. We already saw how this behaved when it came to momentum, and we saw how this was a discrepant event that we were able to use to expand our understanding of forces. But now we're going to use it to understand our explanation of energy. Because remember, in theory, this should keep going. The momentum is transferred back and forth with no problem, and yet it doesn't. It doesn't. Over time, it slows and it stops. How? Well, our understanding of energy says that the kinetic energy of this system was introduced when I used my hand to raise it up. This, when I lifted it, was kinetic energy, it's moving, and I lifted it to a height, so it had gravitational energy. The moment I let go, it fell back down. All of that came from the chemical energy that I ended up burning when I ate some food. But it's slowing since we started here. Why? Something is taking the kinetic energy away. It can't be created or destroyed, remember, so something has to be taking it away. Can you hear it? Maybe you can. It's the sound. You can hear the ball bearings click. Click, 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 click. What does that mean? Every time there's a click, waves of energy come off of this thing in all directions, just like I drew here. Those waves of energy are organized, which is why your ears and brain have the ability to interpret them into a sound, but they are energy that is moving. The particles in the air are moving. It makes me wonder if you guys know how ears work. Inside your ear, there's an eardrum. You've probably heard of this. And the eardrum is like a big drum, hence the name, drum skin. And it moves back and forth really fast. When pressure hits it, your ears are open to the outside air. When I talk, I end up making organized patterns in the air that go out from my mouth, and then they bump into the particles in my throat, bump into the ones a little higher up, bump into the ones a little higher up, bump into the ones that are higher up, and slowly but surely these bumps push through the air until they reach your ear, where they bump into that eardrum. Your brain can then process all of that sound and pick up what's going on. Now, the inside of the ear is a little more complicated. There's like a little seashell structure that's kind of in the back inside, connected to the eardrum, and the seashell sort of has different little hairs, we'll call them. They're like sensors, the receptors, and they vibrate to pick up the sound. Each hair can pick up a different sound, so the mix of all of them allow you to hear more. Of course, right now you can hear more because you're nice and young, but as you get older, those hairs will snap off. And as they snap off, you lose the ability to hear that sound. This is one of the reasons why your parents may have told you, don't listen to such loud music. Because if you do, you damage those hairs. Because so much energy comes into your head that the hairs end up going, and they snap. As a result of that, you damage your hearing. Because all the energy that is coming into your head in order to make it so you can hear was the same as the energy that I originally gave to this. So, is there thermal energy as well? Yeah, a little bit. When the ball bearings hit, they end up heating up the surface where they're hitting because, there's friction, there's blows, they're coming together. And as you know, friction heats things up. That's another way in which kinetic energy can turn into thermal energy, is by two things rubbing together. So the reason this object stops is because there's a multitude of different things that the energy is being turned into. The kinetic energy that I originally gave it turned into gravitational energy in order when I lifted it up, right, like this. Then I let go and it swung down and it passed its kinetic energy back into these, which caused this one to swing up and these ones to swing down, and back and forth it went. And it created sound and it creates heat. All of that originally came because I used my muscles to lift this thing, and I got that energy from eating food. So this energy, it flows around, it moves. And yeah, there's a bunch of math we could solve to figure out how that works, but we're not going to go there. All you need to know is that this energy exists and it transitions from one to the other. So, we're going to leave it there. And I will see you guys next time.